Hi, this video is going to answer the question, why don't we just use arrays? We've described arrays in previous videos. They're a data structure that does work. Why don't we just stick with arrays and be done with the whole topic of data structures? So, remember the array, it's a fundamental collection structure. Pretty much every programming language has an array. It does hold multiple elements. So on that level, it works. However, the nature of an array is that it has a fixed size. When you create an array object, you have to say at that moment how big the array will be, and you're stuck with that. You can't change it. That means that any kind of situation where you need to deal with variably sized data becomes awkward. So if you're writing a program and when you write the code, you don't know how big the array needs to be until runtime, it's going to be a little tricky to deal with that. So another consequence of this is that some common use cases take quadratic time. Big O of n squared time is another way of saying that, and that's slow and slower than it needs to be. What we need are some superior data structures that can handle these common use cases. We're going to go into one in a moment efficiently. And as a preview, the vector is one data structure that can handle variably sized data better, and a linked list also can handle variably sized data more efficiently and more easily. So let me be specific about one use case that is inefficient if you use a plain array. That's reading data of an unpredictable size. So this happens when you need code to read a collection of values, and this could come from user input. So maybe this is an app where people type stuff in, and we don't want to limit, like you're limited to 6 things. We want it to be however many items people type in. Or there's a file. We don't know how many data elements are in the file. We just need to read from the file one at a time until the file ends. Or maybe an API call, you call into some API service and it gives you back a list of things, and we don't know how long that list will be. Or we are reading from a database and we get a result set and we don't know how many rows are going to be in that result set until it comes at us, and so on. There are a lot of cases when this kind of thing happens where you don't know the size ahead of time. Here's a very simple algorithm for handling that. Create a data structure called D that will hold the elements, and as long as there's one more element available, we add it to the data structure D. So that's the simplest algorithm I can think of. Just keep sending them to me and I'll keep storing them until we're done. We do this all the time. This is a bread and butter, everyday thing to do in programming. We want this to be easy and efficient. But if we do this with arrays, it will end up being quadratic time, which is written big O of n squared time, and that's slow. As a preview, this whole operation with a vector or a linked list takes big O of n time, called linear time, which is much faster, and I'll show you how that shakes out empirically in a moment. So here's like a concrete example of that, reading a file. So what I'm going to do is implement this algorithm right here, this while loop algorithm, and have one set of code that uses an array, one set that uses a vector, one set that uses a linked list, and I'm going to measure how long they take to run. Here's a preview of the data. The array version gets sluggish around 60,000 elements, and that's not a lot of data in the modern day, 60,000 things. We make apps that deal with millions or billions of elements, so that's disappointing performance, and it gets worse and worse and worse as you throw more pieces of data at this thing. That's the whole aspect of quadratic growth, that it gets worse and worse and worse as the input grows. So while the array is pretty slow in this use case, the vector and linked lists are fast for any input size I threw at it. This gets at the idea of scalability, that we want our code and algorithms and data structures to scale up to handle larger data sets. That goes into the user experience. This isn't just like we want things to be fast for its own sake because we care about that for some reason, but the end user experience matters here. People are willing to wait maybe a couple seconds. If you're using an app, you tap a button, you expect it to respond in 1 or 2 seconds maybe. So if you tap something and it takes 10 minutes, that's not really acceptable. People aren't going to want to use that. And it also goes into the energy consumption of the code. The more you make the CPU work, the more energy it uses, and that goes into, how much carbon we're burning to produce this electricity and how much it costs to provide the electricity and the battery life of mobile devices. So of course we want to economize that if we can. So let's look at the code. Here's the first version of this program that uses an array. I create an input file stream and I'm reading ints out of this text file. So I'm going to allocate this data array to be an array of length 0 to begin with. It's allocated on the heap. I don't know how big it's going to be, so the stack won't work. And I've got my n variable keeping track of the current length of this array. here's the algorithm implemented in code. So while I can read one int into X out of the file, then we store that int in the array. And we have an issue here that the array is full going into this loop iteration, so I need to allocate a new array that's one element bigger to hold X. I do that here. New data is a new int of length n plus 1, so that makes an array that's big enough to hold X. I need to copy everything over out of the old array into the new one. That's what this for loop does. We want to make sure to free the old array so we don't have a memory leak. And then now data equals new data. So after this code here finishes, what happened is we made a copy of the old array, except it's one bigger. And then data at index n is equal to x. I'm storing this x I just read, n++ to keep track of that bookkeeping to make sure n is accurate. So this works, but it's not very efficient because I have this outer while loop that's repeating n times for each element of input, and inside of that I have this for loop that repeats n times to do all the copying. You have an n multiplied by n makes n squared runtime, which is pretty inefficient. Okay, here's what that code would look like if I refactored it, meaning rewrote it to use a vector instead. Immediately you see it's a lot shorter, which is a good thing. So I open my file, I create a vector of ints called data, and I have the same algorithm. While I can read one more int, then I just do data.pushback. So this is a high-level data structure operation. Pushback adds one element to a vector. I don't have to write out all that code here. And it's out of the scope of this video, but we'll see later that this pushback takes constant time. So I have this loop that repeats n times. Pushback is big O of 1 time. This whole loop ends up being big O of n. The science says this vector implementation should be a lot faster than the array. Finally, just to complete the trio, I have another version that's using a linked list, and we'll get into that in more detail later. The only change between this code and the vector code is changing the word vector to list. This is showing off how we have a interface that we've implemented in different ways. And this one is also fast at linear time. Okay, here I am in a Linux environment. I'm going to show you how this timing shakes out. I created these text files full of random integers, 20k.txt has 20,000 integers and so forth for some other sizes. And what I'm going to do now is run these three different versions. First, the array version. And you'll see on 20,000 pieces of input, not so bad. I can time this accurately with a time command, about 0.7 seconds. You know, that's not too bad. I think people would be okay waiting 0.7 seconds to do something. If I run 40,000 elements through that code, okay, now I'm up to 3.5 seconds. And, you know, that felt like a noticeable lag. I don't really want to wait that long when I execute some command in software. And I don't know, if I go up to 60,000 elements, this feels like a long time to wait for a piece of software to do something so simple as read some data out of a file. Now let's switch to the alternative versions. I've got the vector code ready to go. And if I run this on the 20,000, see, it's done in 0.009 seconds, already quite a bit faster than 0.8 seconds, you know, almost 100 times faster. And if I go up to 60,000, where we were waiting for 9 seconds with the array, this took 0.009 seconds. See, that it's basically done as soon as I start it. Doesn't really matter. And if I go all the way up to 200,000, still 0.13 seconds. So this is that scalability factor I was saying. The array version is pretty slow. It doesn't look good. It's getting slower and slower, but the vector version is just snappy. It's fast no matter how many elements I throw at it. And the same is true for the linked list version. Here's that data in a graph form. What I did was run all three versions of the program on various sizes of n, the number of ints, and plot this with a line graph. And what you can see here is that the blue line, that's the load array performance, is getting faster and faster. The elapsed time is the amount of time it takes. Larger number is worse, it's slower. And you can see that that blue line for load array is much higher than the two alternatives, and it does have a quadratic shape, meaning it's getting slower and slower and slower. So that's very poor scalability. By contrast, load vector is in red down here, load list, linked list is in yellow, and they're so low that they're even hard to find on the graph. And that's because that's a linear pattern there. The amount of time that they're taking is scaling up a little bit as the input gets bigger, but is proportional to the input size. And they're very close, so they're hard to tell apart. Load list is a little bit higher than load vector because linked lists are a little bit slower than vector, but either one of them is vastly faster than the array. So that's why we can't just use arrays. We need to use these more sophisticated data structures of vectors and linked lists.